Comrades, hello! We need to pick up the pace. This episode will explore the nuclide identification capabilities of the KC761X. This installment features some additional props. Here we have a box of high-purity lanthanum oxide powder. Many rare earth elements contain naturally occurring radioactive isotopes. Their concentrations are very low, but the 761X has high sensitivity and can detect them. These materials can be purchased legally. Next up is an old friend of ours. This is called an ionization smoke detector. Inside is a tiny radioactive source. This can also be purchased legally. You can buy this module directly and disassemble it. It's illegal under some foreign regulations, but our country doesn't seem to have relevant rules. So we've already taken it apart. And this thing here, it's an old military anemometer. Many of these old military instruments used radioactive luminous paint. Radium is a potent alpha-emitting nuclide, emitting alpha particles. Then, when bombarded with alpha particles, fluorescent materials like zinc sulfide emit light. However, the destructive effect of alpha particle bombardment is extremely significant. Therefore, despite radium's long half-life, these fluorescent materials typically cease to glow within a few years. These old devices, whether anemometers or radio voltmeters, aircraft instruments, with switches with luminous indicators, may contain this radioactive nuclide. After powering on, it may have been used previously. This instrument is currently set to measurement priority mode. If you need to perform nuclide identification, we need to switch it to energy spectrum mode. Press the mode key. Then select energy spectrum priority. Nucleus species identification involves analyzing the energy spectrum to determine possible radioactive isotopes. If characteristic peaks for a specific isotope appear on the spectrum, then that isotope may be present. However, this isn't 100% certain. Several scenarios are possible here. One is the presence of energy or characteristic peaks, universal peaks, which may be shared by numerous nuclides, such as the 511 cuff positron-electron pair annihilation peak. Additionally, in the low energy range, such as below 100 cuff, many nuclides exhibit characteristic spectral lines here. However, since the 0 to 100 cuff range is only this narrow band, these nuclides are densely packed within it, making them difficult to distinguish. Furthermore, some nuclides possess only a single characteristic peak. It's quite difficult to judge. The identification of KC761X isotopes is divided into manual identification and automatic identification. Three types. Manual identification refers to using a cursor to manually remove finding feature peaks if the cursor is at a certain position, a characteristic radiation of isotopes. Then the cursor's indicator will be displayed. Name of the nuclide. Now everyone is seeing the spectral priority mode. The top menu, divided into cursor, proportion, trace control, and advanced. Generally speaking, when approaching the area to be identified before material, you need to use the clear function within the trace control feature to erase existing curves. Otherwise, you won't know if it's accumulated spectra from the past or from the source being tested. Next, use the cursor, which includes peak finding and left drag cursor movement. Let's move the cursor to observe. Position the cursor here. The first number shows the cursor's energy, followed by the count rate at that position, and the nuclide corresponding to that energy. The position where the cursor is placed, if a corresponding nuclide exists, it will display the characteristic peak of that nuclide. The prompt line is this vertical dashed line. The height of the prompt line indicates the emission probability of that nuclide at the energy level where the prompt line is located. The higher the prompt line, the stronger the radiation at the energy level. Where the prompt line is located should be. However, since our instrument exhibits lower sensitivity at higher energies, if a high energy hidden line shares the same height as a low energy hidden line, high energy peaks are often lower than low energy peaks. Based on the current spectral lines, can we say there is lanthanum 176 indicated by the cursor? No. because no characteristic peaks appear on these major spectral lines. This region is primarily low-energy noise. There is no peak at the cursor position. Typically, for reliable nuclide identification, we need to accumulate data over a period of time to achieve a smoother curve. This is especially crucial when the energy of the nuclide to be identified is relatively high. Due to the lower sensitivity at high energies, longer accumulation times are required. For instance, detecting potassium or 40 in the environment may necessitate over an hour of accumulation. Currently, only slightly over 5K counts have been accumulated. This accumulation is insufficient. Let's examine. If genuine lutetium-176 is present, what its characteristic peak would look like. Let's bring in the lutetium-176 sample. We can observe the count rate suddenly jump from the previous dozen or so CPS to 80 or 90 CPS. After approximately 1 minute, the count had exceeded 10K. At this point, the prominent peaks of the two characteristic features had become distinctly visible. Additionally, two other characteristic peaks were discernible with at least one clearly observable. The greater the number of precisely matching characteristic peaks, the more reliable the identification becomes. At this point, manual interpretation can confirm that the measured radiation source indeed contains lutetium-176. Thus, the automatic nuclide identification above has also detected lutetium-176 if the cursor is not aligned with the characteristic peak displayed on the spectrum at this point. The cursor's hidden line remains visible, only now indicating a different element. Return to cursor peak search. After searching to the right until the end, it will automatically jump to the far left. Alright, the first peak. Here is a hidden line, and there appears to be something resembling a peak, displaying a nuclide. However, this shape at low energy often cannot be considered a peak. The likelihood of this nuclide is very low. Check the second one. The second one is 55 curve. It could be americium-241, but the prompt gamma pair isn't quite accurate. We should remain skeptical about the presence of americium-241. Now examining the third peak. Lutetium-177 appears. Lutetium-177 also shows detection lines. One or two lines overlap somewhat. But this primary characteristic peak is not aligned perfectly. Continuing, at this point, three peaks are perfectly aligned. Lutetium-176, therefore, Lutetium-176 is the most probable candidate. This is why manual interpretation requires a certain level of experience and also carries the possibility of error. Typically, one should maintain a degree of skepticism toward identification results and make a comprehensive judgment based on the on-site environment and characteristics of the tested sample. The instrument also features an automatic identification mode. This method relies on the program to automatically locate peaks, automatically queries the database to match the detected peaks with corresponding nuclides. Now let's place our anemometer, as seen in older military equipment. The usage was quite substantial. At the time, little attention was paid to whether it was safe or not. Due to the high radiation intensity, it quickly accumulated to 30 or 40,000 counts. At this point, automatic identification became possible. It identified radium-226 and also identified barium-133. I find this barium-133 result questionable. Now we'll perform manual verification. Similarly, search for peaks to the right. Alright. Here we find the first peak for radium-226. Numerous reference lines will appear. These reference lines show high alignment. Thus the likelihood of containing radium-226 is very high. We continue searching for peaks to the right. Here is a peak for lutetium-176, but it aligns poorly with the reference lines. So the probability of lutetium-176 is low. One peak of radium-226 and one peak of indium-111 are nearly overlapping. Thus, a single hidden line appears that can completely correspondence, but other areas where reference lines should appear are absent. Where reference lines exist, peaks should be present but are missing. Therefore, it cannot be indium-111. Gallium-67 is also absent for the same reason mentioned earlier. It is not present. Then barium-133 is present because this peak exists. So the instrument detects barium-133. Let's take a look. One peak height matches perfectly. The other two peaks are still quite close. So whether barium-133 is present, I find it questionable. The symmetry alarm has just triggered. After the instrument alarms, press any key. The alarm will pause for 1 minute. Typically, low energy readings hold little significance. As environmental background radiation contains numerous low energy rays, however, our current peak far exceeds the environmental background. This indicates the genuine possibility of some low energy nuclide being present. Next, we'll examine the Americium-241. Since we've been using the radium source for an extended period, over 200 C has already been emitted. Default spectra are uncleared. Adding a new one with over 300 CPS count rate requires significant time to extract characteristic peaks. To make the characteristic peaks stand out will still take considerable time. Therefore, it's best to clear the spectrum before performing new identification. Let's observe here how long it takes to identify without clearing. It seems this area is newly emerging. As a distinct feature, this part is becoming quite prominent. Americium-241, we use the cursor to identify it again. Regardless, we can keep searching for peaks to the right. Because there are only so many peaks to begin with, this instrument only searches for peaks to the right. This single button, we just press it repeatedly. Alright. A peak appears here, and the cursor has located it. Here at 59.42 cuff, meaning Americium-241 is indeed present here. It can detect Americium-241, but at this point, if we don't know for certain that Americium-241 is present, we should still proceed with caution. Because Americium has a prominent characteristic peak at 59 cuff, while its other peaks are scattered across the 10 to 20 cuff and 20 to 30 cuff ranges. Here we have a large cluster, and this segment contains numerous other potential interfering factors. Let's demonstrate again what happens when we clear the spectrum for recognition. How about it? After clearing it, we bring it back. It identified Americium-241 in under 5 seconds total. Therefore, after clearing the data, for nuclides with relatively concentrated energy, the speed will be faster. However, some nuclides have highly dispersed energy, such as thorium in the environment. In such cases, accumulating a very high count number is necessary to obtain a relatively perfect spectrum. The longest wait may exceed 1 day. For situations requiring prolonged waiting, power supply stability, it's best to connect an external power source. Additionally, it's worth noting that all instruments may have measurement errors. It may also drift over time. 761 may also experience energy drift. Instruments are calibrated using the energy of nuclides as the standard. The energy of gamma rays emitted by the same gamma nuclide remains constant forever. That is, if you know the measured substance will produce a characteristic peak at a specific energy, then this peak can serve as the gold standard for calibrating the instrument. At this point, you can use your own Americium-241 and natural potassium-40S2. Perform energy calibration on the instrument. Ensure the instrument is properly calibrated. Relatively speaking, the KC761C and 761CN exhibit very minimal drift, typically not exceeding 1% per year. Of course, we acknowledge instruments may have errors, just to give you an idea of this concept. But in the vast majority of cases, they remain quite accurate. That concludes our introduction to nuclide identification. For today, thank you for watching. Goodbye.